All right, this is it, the culmination of our circuits unit, what everything has been building towards. So in this final lesson, we're going to be talking about analyzing complex circuits and putting together our understanding of both Ohm's law and connections between resistors in series and parallel to try to understand how voltage and current get split throughout a complex circuit. Now, before we get started, just a little bit of review of some of those key terms that are just coming up again and again throughout this lesson and this unit as a whole. So current, again, as a reminder, is just the rate at which our charged particles are moving around through our circuit or through one part of a circuit. Resistance then describes anything that serves as an obstacle to this current, anything that slows our current down, kind of like an electrical friction. And that's going to be a useful picture to have in your mind later during this lesson. And finally, voltage, maybe the most conceptually tricky of the three, really gives us a measure of how the energy of our charges is changing as they move throughout the circuit. So it's telling us, first of all, which direction they'll move, because we know that our charges will tend to move from high to low energy, much like objects falling in a gravitational field. But then voltage is also telling us specifically how much energy they're losing as they're moving throughout this circuit. So let's hang on to those and get going on this. So a few key patterns that I hope that you were picking up in the investigation that you did in class. So first question for you is, do all parallel paths always have the same current running through them? The answer is not always. Sometimes, if you have the exact same resistance on two branches, then they're equally desirable to the current and the current will split evenly between them. But we do generally find this pattern that if you have a path with greater resistance, less current is going to go down it, and vice versa. If you have a path with less resistance, it's going to get greater current. Kind of like those grocery store checkout lines. If you've got a slower checker, kind of like a greater resistor, fewer people will go into that line, but some still will. Right? Now, if I consider a junction where current is splitting up, right? If I take all the current that's going into the junction, it had better be true that that's equal to all the current that's coming out of the junction. We call this the junction rule because it's about junctions, okay? Which basically says any current going in has to then come out at some point, which hopefully makes some intuitive sense. It's kind of like if you think about, instead of current, you're thinking about cars going into an intersection. If 3 cars go into an intersection and only 2 come out, there's something weird about that intersection, right? We're expecting anything that goes into the intersection has to come out. That's the essence of this junction rule. So just to check in on this, I've got here a circuit with 3 different parallel pathways here. And so based on the information given about how current is flowing through the circuit, my first question is, what current must be flowing through that last resistor on the far right? Well, according to our junction rule, any current that's going into a junction has to then come out of the junction. So what I'm seeing is that 3.5 amps is being drawn from the battery and all comes together until we reach this first junction. And then our current splits 3 different ways. I've got 1.5 amps of that current going down through this first resistor on the left, and then another 1.5 amps going through the middle resistor. And so in order for us to have the same total current going into the junction as is coming out of it, that leaves a remaining 0.5 amps of current that must be coming through that final resistor on the far right. Because 3.5 is equal to 1.5 plus 1.5 plus 0.5. Okay, so everything adds up. I haven't lost any charges or created any charges out of thin air. Second question is, how do these resistors compare to each other based on this information? Well, what I notice is that these first 2 resistors have the same current going through them, so they must have the same resistance. But this last resistor on the far right has much less current, which means that it must have greater resistance than the other 2 resistors do, because that's why we have less current going through it. It's sort of a less desirable option because it must provide a greater obstacle to our current, must be slowing our current down. Let's keep going. So a few other patterns from our investigation. Did you find that voltage changes along a wire? The answer should hopefully be no. Voltage will only change across a resistor or a device that serves as a resistor. And the bigger the resistance of the device is, the bigger the voltage drop will be. Now, to make conceptual sense of this, let's go back to our analogy that resistance is like friction. So we know that friction can cause our kinetic energy to dissipate and turn into thermal energy, etc. Right? Now, a wire has very, very low resistance. So it's essentially like a frictionless path. And if you imagine sliding along a frictionless path, you're not going to be losing a lot of energy. You get to kind of hang on to your energy. And in the same way, the charges as they move through this low resistance wire are going to be able to hang on to their energy. But once they hit that resistor, it's like hitting a rough, high friction patch on the ground, where then you're losing a lot of energy to thermal energy is the main one, but it depends on your device. If your resistor is a speaker, then you're losing it to sound energy. If it's a motor, you're losing it to kinetic energy. It could turn into a number of different things. But the bigger the resistance is, the more of a voltage drop we're going to see across that device. Now, if I consider any complete pathway around the circuit from the high potential side of my power source to the low potential side of my power source, and I take all the resistors along that path and add up all of their voltages, what I should find is that they add up to the voltage of the power source. We call this the loop rule, that the sum of all the voltages around any complete path around a circuit should add up to the voltage of the battery. All right, and that's true for as many different parallel pathways as we have. So just to check in on this, we've got 3 resistors in series. The first resistor has a voltage drop of 4 volts. The second resistor has a voltage drop of 6 volts. What must be the voltage drop across that final resistor? Well, according to the loop rule, the voltages for all 3 of my resistors has to be equal to the voltage of my battery, which is 12 volts. So 4 volts plus 6 volts, I've got 10 volts so far, but I'm going to need another 2 volts of voltage drop across that last resistor for the loop rule to be obeyed here. Now, based on this information, what can I conclude about the resistance of each of these resistors? Well, the more resistance a resistor has, the more energy it's going to dissipate, the bigger the voltage drop is going to be, which means that my resistor that has the biggest voltage drop must have the biggest resistance, must be the biggest obstacle to the current, and therefore dissipating the most of its energy. Whereas my 2-volt resistor must have the least resistance as well, because it's not dissipating as much of our electrical energy away. A couple other key patterns for us. If I have 2 resistors in series, they're always going to have the same current. And we talked about this earlier in the unit about how current is kind of like traffic on the freeway, and as you add more resistors in series, they're gonna kind of create that backlog and slow down current both before and after. So any resistors in series have to have the same current going through them. But 2 resistors in parallel, on the other hand, always have the same voltage. And this kind of goes back to that loop rule, that all pathways around the circuit, even 2 parallel alternative routes around the circuit, have to still have the same voltage drop. And a way that you can kind of think about this is going back to our gravitation analogy. Instead of going around a circuit from high electric potential energy to low electric potential energy, think of going down a mountain, from high gravitational potential energy to low gravitational potential energy. There might be a bunch of different possible pathways down the mountain. Some of them might involve like nice, happy, gentle staircases. Some might involve like huge jumps and major changes in elevation. But at the end of the day, regardless of which path you take down the mountain, you better have experienced the same total change in elevation. Whether you did it in big jumps or in small steps, ultimately, from start to finish, you have to have the same change in energy. And that's the idea behind this loop rule as well, that regardless of which pathway around the circuit you take, you better still have the same total voltage drop, and therefore the same total amount of energy loss during your journey around the circuit. Couple last patterns for you. So whether we're talking about the circuit as a whole, or one individual device within the circuit, we should always find that voltage, current, and resistance are related by Ohm's law. Ohm's law shows up over and over and over again in every single circuit. And so we can apply Ohm's law sort of at two different levels to our circuit. We can apply Ohm's law at the level of the circuit as a whole by saying that the voltage of our power source is equal to the total current being drawn from the power source times the equivalent resistance of the whole circuit. Okay, so that's Ohm's law at the whole circuit level, but then also zooming in on one individual device within the circuit, the voltage drop across a single resistor is going to be equal to the current running through that resistor times the resistance of the resistor. I just said resistor a bunch of times, but you get the idea, all right? So Ohm's law holds for an entire circuit. It also holds for one individual device at a time. Now, with all of these different patterns, we can predict exactly how current's going to split through a circuit, how voltage is going to split throughout a circuit, and where we're going to see the biggest energy losses. But that's kind of a complex process to try to put it all together. So here is my handy step-by-step guide for analyzing circuits, all right? First step, I told you it was going to be finding the equivalent resistance, and what do you know? It is. All right, so first thing you got to do is find the equivalent resistance of the circuit, and if you haven't been redrawing the circuit after each step of this process, start doing it now. It's really going to save you a lot of pain if you're doing that. Okay, so equivalent resistance first. Second, once you've got that equivalent resistance, you can plug it into Ohm's law using the voltage of your power source to find the total current that's being drawn from your battery. And then the third step, which is actually a bunch of steps over and over again, is to now work backwards through all of those drawings that you did while you were finding the equivalent resistance. And from there, you can use Ohm's law to solve for the voltage and current of every single resistor along the way. It may involve multiple steps, but each step will be relatively small, and we can get you there. Right? Now, as you're doing this, one key thing to bear in mind is that resistors in series will always have the same current as each other. Resistors in parallel will always have the same voltage as each other. And if you'd like to check your work, and I highly recommend that you do, you can then apply the loop and junction rules to make sure that your work is all copacetic and everything's working out for you. All right. Final check for understanding. So I've got this circuit right here with 3 resistors, a combination of parallel and series. First question is, what equation relates the current running through resistor 1, resistor 2, and or resistor 3? Well, according to our junction rule, all of the current that enters this junction after R1 and R2 must be equal to the current leaving that junction, or in other words, the current running through R1 plus the current running through R2 is equal to the current that then ends up getting funneled through R3. So I1 plus I2 equals I3. Second question, what voltages in this circuit added together will be equal to the voltage of the battery? Now, there are 2 correct answers for this one. According to the loop rule, any pathway, complete pathway around the circuit should have a total voltage equal to the voltage of the battery. Okay. Now, there are 2 complete pathways around this circuit. One is to go through R1 and then R3. So that means the voltage across resistor 1 plus the voltage across resistor 3, that had better be equal to the voltage of my battery. But also, another complete pathway around the circuit is to go through R2 and then R3, which means that voltage 2 plus voltage 3 should also be equal to the voltage of the battery. And that's all I got, folks. Thanks for tuning in.